All right, so here we go. Unit 4, Lesson 2, Einstein's special theory of relativity. All right, we're going to dive into Einstein's most famous principle. He actually got E equals mc squared from this and from these ideas. We're going to discuss that as we go through these next couple of days. Now, we're not going to understand all the mathematics of this. It's 4 days on a super complicated topic. But that's okay. All right, the worksheets and things don't reflect the mathematics. They're more of a conceptual level type thing. They don't dive into it. Just a taste to get you interested. See, hey, you like something that's a little bit over our head, but it's really fun to think about and talk about. So, now, before we dive into Einstein's special theory of relativity, what that means is it's the special case, special exception to relativity. It doesn't work like it does everywhere else. Before we get into the special case or special theory of relativity, we need to talk about what relativity is. Okay, so this is the idea of relativity. Speed is a relative quantity. It's based on your perspective or your frame of reference. Okay, here's my example. Here's my first example. I'm going to give a bunch of them. All right, so you're sitting on a corner and you're going to watch a school bus zoom by. While the school bus is zooming by, you see a boy that's in the back of the bus stand up and move to the front of the bus to throw away a piece of paper. Does everybody know? Everybody's done that at some point. You've walked on a moving bus.
Yes.
Everybody's done it? Okay.
See, yes.
All right.
I'm done moving.
Now the girl sitting on the corner sees the bus go by at 10 meters per second. If the boy gets up and moves at 2 meters per second, who does the girl that's sitting on the corner see who's going faster? Who's actually going faster, the boy or the bus?
Boy.
The boy is actually going faster. You'll see the boy actually start to pass the bus in the window. So how fast does that mean the boy is going? 12 meters per second. See how that's relative and how you can speed up? Now, if you're on the bus and that's your friend that's going up to throw your trash in the can, how fast do you see the boy going?
2 meters per second.
2 meters per second. So from one perspective, the boy's going 12 meters per second. From the other perspective, he's going 2 meters per second. Who's right?
They both are.
They both are. That's why it's called relativity. They both are based on perspective. Now that's not some out there statement that's saying, anybody whoever that is, whatever you say is right. No, it's based on your perspective. It still has to make sense. Yeah.
Okay, theoretically speaking, if the bus was going the speed of light and the boy moved forward, would he be doing faster than the speed of light?
Yes. Anyway, we'll be talking much about speed of light.
Broke physics.
Zay broke physics.
What happens if you're moving at the speed of light and you turn on the flashlight?
The problem with moving at the speed of light, which we are going to be discussing at great length, the problem with moving at the speed of light is that anything that has mass, the mass grows way out of proportion to what it is at normal speeds. And so the faster you go, the mass itself will increase to the point that it becomes infinity large as you approach the speed of light. And so basically you become more massive than the entire universe the closer and closer you get to the speed of light. What you need to do is you need to learn how to turn yourself into some sort of electromagnetic wave, thus you become massless, and then at that point you're going to the speed of light. Hey, guess what? They're doing it at the atomic level right now. They're taking atoms, they're scanning them, they're sending that information through an electromagnetic wave, and then they're reconstructing that exact atom in another location.
Whoa,
Transportation.
That's probably one of the only legitimate, that's one of probably the most probable Star Trek type things that could actually happen. They're actually working on that. All the other stuff, no. So. Everything like that works really well at the atomic scale, but when you try to scale it up, it just doesn't work. All right. So the speed Speed of the boy in perspective of the girl, we need to get this in our notes. 12 meters per second.
And then 2 meters per second.
Yeah, and then 2 meters per second.
I think it's supposed to say 10.
Another example of relativity, this link here on this webpage doesn't work. So let me give you a couple more examples that I didn't put on here. One of the examples that I always like is, have you ever flown in a jet? You're going well over 700 miles per hour at times. Have you ever gone to go to the bathroom?
Yeah.
Oh.
Not very fun.
Do you need to go 702 miles per hour to get to the front of the plane or the back of the plane to go to the bathroom?
No.
Yes.
No. You just walk up and you scroll your way back there. You just, whatever, I gotta go. So you just scroll your way back there. You scroll
Can't do
it
much
up.
scrolling when there's a lady
Now,
with the car.
but from an outside perspective, how fast are you going? Let's say you're coming from the bathroom in the back of the plane back to your seat. How fast would it look like from somebody outside the plane? You're going faster than the plane. Because you are. But you don't have to adjust yourself for that. It's kind of like when you have a fly come. You ever thought about this? You ever get a fly inside your car once you're already sped up? Fly, you're going like 70 miles per hour down the interstate. Fly comes, he's like buzzing around your head. You ever had that happen?
Yeah.
Can a fly go 70 miles per hour?
No.
No, he doesn't have that ability.
Steroids.
The fly on steroids.
I have nothing to say about that.
I feel like it would kill them.
Yeah, I'm sure that would work.
It's super flat.
You should have tried that during your biology ISP. So.
Yeah, Griffin.
If
If I was that creative then,
That fly doesn't have to adjust himself to the car's speed because he's just, to him, when you're going at a constant velocity, all physics works normal for you. Yeah, everything works. You don't have to adjust yourself to how fast everything else is going. You just walk and go. Neither does that fly. He doesn't have to go. So he already got sped up with your car. And then once you're going at constant velocity, he flies around like normal. He doesn't have to go 72 miles per hour to get up to the front windshield. Yeah, Bryson?
Okay, let's think of the bus or whatever. What if you're walking to the back of the bus?
You would be going slower than the bus from an outsider's perspective.
you'd be going 8 meters.
From an outsider's perspective, you'd be going 8 meters. You'd still be going forward, okay? If you're driving a bus from an outsider's perspective, you're still moving forward, just less than the bus, so it looks like the bus is passing you.
What about from the perspective of someone in the bus?
From in the bus, they would see you going at -2. They'd be seeing you going at just -2 meters per second.
Physics.
Just a matter of perspective. Have you ever thought about it like this? If you're driving along in a car, you're going 55 miles an hour down the road, and you see a telephone pole, you're driving this way. Which way does the telephone pole move? That way. And how fast is it going? If you had a speedometer, how fast would you clock it going?
0?
As fast as your car is.
55 miles per hour.
But it doesn't.
If you hit that pole, going 55 miles an hour, it'd be the same as if that pole hits you going 55 miles per hour. Same thing, same physics would happen. All the same thing would happen. Just a matter of perspective.
You did.
Technically, that's why back 400 years ago, there was such a debate. Was it us spinning around the sun or the sun spinning around us? All we see is what? This big globe going like this across the sky. Was that right? Is that east and north? Yeah. No, actually it goes like this. Big globe going across the sky. No. It was the way the first one.
Rises in the east.
Rises in the east, that's why. So it goes like this, right? Across the sky like that. Which is moving? The sun or us?
Well, obviously.
We're both moving, actually, you're right. But we understand that now, but then how would you know unless you could go outside your perspective to tell which one? Now Newton did, and so did Galileo, and many others. And eventually they realized that it makes better sense that we're revolving around the sun.
Well, for a while.
Blasphemy.
It's been flat land.
Well, throughout the whole thing. Where did the pole of the car and at least spot the windshield? Because our own
Because of
course
momentum.
didn't stop.
Well, that has to do with acceleration. Relativity doesn't work like that in acceleration. When you're going to speed up for the airplane, right? When you're getting ready to take off, you feel funny, right? There's a lot of things going on there we'll talk about, especially when we get to roller coaster physics. But you know, when you feel you're getting ready to take off, and you know you feel like you're getting slammed in this seat, right? And your stomach feels funny. Because what's happening is your guts aren't attached to your bones all that tightly, and so your bone structure is moving forward with the plane, but your guts want to stay where they're at. And so when you go forward, your guts slam into the back of your rib cage and things like that, and you're like, "Wee, this feels so good! I love this."
But it's not G-force working against.
Well, we'll talk about G-force. We'll have a whole several days on G-force, specifically before Six Flags.
Well, if you're in space, can't the G-force be so strong that it actually crushes your legs?
You can do that here. You can do that on Earth. G-force. That's why anytime you get crushed, it's because the G-force is way greater than your body can handle.
Well, I mean, but if you're going at a high speed, like if you're going like the speed of sound, don't you ever?
We're going well over the speed of sound right now. Did you know that?
Yeah.
From what perspective? Are we going well over the speed? We're going like 13,000 meters per second. From whose perspective?
Hey, well then
The sun's perspective. We're flying around the sun, but does it feel like we're going that fast?
Is he gonna drop raisins and cornflakes on us?
Dan's got his hand up for a long time. Dan, go ahead and ask your question.
Okay, so we're orbiting around the sun.
Yes.
And in space, there's no gravity or anything. So once you're going in a constant direction, you keep going.
There's gravity.
There is?
The sun's gravity is
The sun's
keeping us in a
gravity
circular
pulls
orbit.
us. And is gravity there because of the Earth's magnetic poles?
No.
It's because of its mass.
It has to do with mass. We don't know what it is at the unseen space. If you go up with us, if you take advanced physics, when you go to Fermilab next year, and you ask one of the top physicists in the world what gravity is, they'll giggle at you.
Okay, but I'm not done yet.
We don't know.
So what sets our speed around the sun?
It's a mystical force.
That has to do with our initial velocity. Because when we came into the sun's orbit, there was the best idea was there was some sort of collision, and we got shot into space, and then the sun's gravity well sucked us into it, and we're forever going basically the same speed.
If we ended up in the sun's gravitational pull,
We are.
Does
Which
that mean at one point when the Big Bang happened that the Earth was just a rock and then it ended up by the sun and got sucked into it? Like there was just a rock
Well,
floating through
we're
space?
quite a bit after the Big Bang, which we will talk about the Big Bang. It's about 14 billion years ago. Because Einstein's idea, do you know who came up with the Big Bang?
Sheldon who?
No. Einstein did. And I'll talk about that in just a little bit if we have time today. If not, we'll just write your questions down. We will at some point in the next few days talk about the Big Bang.
We have 18 minutes.
So the Big Bang came from this set of equations, actually. Yes.
when did Einstein die?
All right.
It irritates me about you too.
All right.
It's like you have good people.
Does it rustle your
Hey, Zay, just write your question down, and we'll just write the question down.
Yeah.
If I have time at the end, I'll cover it. And again, some of your questions I'm just going to defer to the end. Till another day, because a lot of this we'll be talking about. Now, the idea of relativity was the first thing that we need to introduce today. The next thing we need to introduce is Einstein's view of space, of four-dimensional space. All right, we're used to our normal three dimensions, which we got forward and back. Right? If I was a one-dimensional creature, I would be on a computer. I'd be a dot on a computer screen that just moved forward and back. Now, the next dimension is left and right. So I'm not confined to just forward and back. I can turn and go to the next one. Now watch this. I'm going to take an interdimensional leap.
Interdimensional.
And yes, the pun is intended. Ready? See? I just jumped out of the second dimensional plane into the third dimension. Albeit not very long, but I was in the third dimension.
How do you get to the 11th dimension?
Well, That's a little bit more difficult.
Diagonally.
That dimensional jump is not quite as easy.
Set yourself on fire.
And then sacrifice yourself.
This is on video. I can't answer. Because I could possibly sue if you actually did that. So no, I do not condone setting yourself on fire in any way. I'm officially on the record. All right, so you got forward and back, left and right, up and down. That makes up what we call space, 3 dimensionals. There's a fourth dimension that we need to take into account, which is we're moving right now. You're all sitting there, right?
Yeah.
Right now, you're moving through the fourth dimension. Time. Time.
Yes!
You haven't stopped.
Yeah, great.
You have not stopped. Even while you're sitting there, like a slug, playing your Xbox. All right?
Yeah.
All right? Your fingers are, like this or whatever.
But you're physically engaged
But-
in your mind.
But you're actually moving. You can actually make an argument to your parents. They're like, you haven't moved in days. Tell Christopher, you haven't moved in days. I have, Mom. I'm moving through time. There you go. See how that works out for you.
So use your physics a little bit.
She said that you haven't moved in 3 hours.
Go do something else.
Yeah.
All right. Now, when we measure events, Dan, you might just want to write your question down.
Okay.
I want to get through the lecture, and then if I have time, I'll take questions.
We always
When-
have time.
You're talking about your direction, you need to take into account all the events and when they occur. Okay, so for example, my apartment address. So I lived at 555 North Generic Lane, apartment 311, June through August 2006. Now that just took into account all 4 dimensions because you got your intersection, you got your street, got your house number, you got 300 levels, so you knew how high you are, and then it gives you a date. Gives you a date. All right, so we got to again consider those things like that. All right, now
Didn't live there.
time is an incredibly important dimension. If we didn't have time, everything in nature that's ever happened would all occur in one infinitesimally small blip. From the moment you were born to the moment you die, everything just happened at once.
What if we are in this blip right now, and then you just perceive it as very, very, very slow?
I don't.
We are in that blip right now, Zay.
I don't know how to feel about this class.
We're in a blip.
I know the mind can handle it.
All of the point is though, is to say, all the point I'm making is that time matters.
But if we're
Time matters. All I'm saying is that within the fabric of our movement, woven within our movement is time. They're all linked. All right, you can't have space without time.
How did we figure
You
out?
can't have time
Okay.
without space.
How did we figure out time?
Time.
The sun? How did we figure out what time?
All right.
By the
Time.
There's a terrible answer.
Time is based on cycles.
Right.
Okay? So how we measure our time is based on our movement around the sun and our movement around our own axis. Okay? And that's how because it's cycles, something that's repeatable. Anything that's repeatable, we can use to measure time. For humans, our heartbeat is about, basically, is our clock. Okay? So, I told you why YouTube freaks me out, right?
Yeah.
All right, you're starting, because every time I look at the ticker thing, all right, here's the end. This is the way my life is. Every time my heart beats, this thing moves just a little bit closer. Except I don't know where the end is, and that's kind of scary. Not only is there that, our whole Earth has a YouTube time ticker.
So you have a fear.
Our sun has a YouTube time ticker.
You're terrified you're gonna get like the low, like the stop and load, where you have to like refresh. You buffer.
If you're in a coma.
You're buffering.
All right.
Physics is scary.
I feel like Brennan's going to be like really funny. All right. Einstein had 2 questions that he asked, that he proposed. Now, again, these questions are important. They actually go into philosophy or religion. Okay? Now, I'm just going to make a disclaimer right away. Is I'm not trying to convince you one way or the other whether you should believe in God or not believe in God. I believe that's not a testable type of thing. Okay? Because one way or the other, it still takes faith. If you believe in God or not, it still takes faith. You have to believe one way or the other, or not at all. You can actually go in the middle. That's fine. I'm not trying to convince you one way or the other. In our politically correct curriculum, we vanilla everything and we take out all the fun. Okay? Because there's 2 things in the world that make people angriest the most. It's politics and religion.
Yeah.
Oh my goodness. So, if you have a major problem with something I say, just come talk to me after class. Okay? And I'll be more than glad before or after school to talk about any of your personal views or my personal views or things like that. In the class setting there in front of everybody, I'm not going to go in depth on those. But I am going to present other people's ideas and what they believe and how it shaped how we get these things right here. So don't be offended by that. Or if you are, just come talk to me. It's okay. It's not a big deal. All right. So he asked 2 questions, which aren't necessarily answerable by science, but definitely shape this. And that is, was there space before the universe came into being? In other words, was there places you could move around? Okay? And was there time before the universe? In other words, was there always a clock ticking somewhere? In other words, was time continually moving some point?
This is going to hurt my head.
This is what he said. This is what he said. Space and time only exist within the construct of each other. What makes up our universe. Space and time are both part of that construct. If you don't have space, you don't have time. If you don't have time, you don't have space. Okay? Now, this is different than the worldview at the time. Alright, this is actually different. Alright, because Einstein, what this was is really radical. Okay, because at the time, the scientific thought of the day was predominantly atheistic. Does anybody know what atheistic means? What's that mean?
You basically don't have any belief in a God or in just anything. After you die, it's just nothing.
Right. There's no God, essentially. Okay.
Straight up.
That was just right. It always was. It always will be. From one, you know what I'm saying? Everything stretches from a negative infinity one way to infinity the other way. Time, life, and so when you're done, you're done. That was the predominant thought. Einstein came along and said that. He said that, okay, there was a time when there was no time. There was a time when there was nothing. He actually went crazy for a little while. You know why he went crazy for a little while?
Because he broke physics.
He did break physics in a really good way.
He was afraid of
When he came up with his equations, he thought he essentially proved the existence of God from that time period. Because at that point, he proved there was no time. You know what I'm saying? Like, he proved there was nothing, and then there was everything, which is called the Big Bang. Do you see why that was a very controversial thing, how that would point to there's a God. He actually, at that point, he was not religious. He was actually Jewish heritage, but he did not, I don't think he in any way, actually I read his biography, in any way he did not follow their tradition. And morality said it all. He was actually not a moral person at all. He's actually very immoral according to the Jewish law. And nor did he have any thing. He basically became an agnostic after that. In other words, it's the middle ground where, okay, there's probably a God, but which one, I don't care.
You just got
And that's not, let's say this, not all agnostics are, I don't care. It's more, whatever, you know, we don't know. And he didn't, that wasn't his pursuit of his life. Fun fact of the day, he actually married, he actually had to divorce his first wife because he was carousing. Because he got really, really popular. And in the day, it's like scientists in that day, like when he got popular, he actually marketed himself. So he's going to, just like an NBA basketball player would, or something like a football player. He got all kinds of people like giving him money to do advertising, things like that. He's one of the #1. He makes more money being dead than like most of us ever see. Seriously, his name, his estate still gets tons of money because of all the trademarks he has.
Einstein.
Every picture you see of Einstein, or every quote, somebody's getting paid for that.
Who's getting paid?
Well, his estate is whoever is great grandchildren or whatever.
Einstein.
Yeah.
Would you say they have more money than Bill Gates?
No.
No.
If they invested wisely. All right. Here's another. We'll go into Big Bang in more detail. Big Bang was an interesting idea. A lot of religious people I know don't like Big Bang because they think it, goes against who God is. I think what it is why it's offensive. Is a lot of people are literalists, 6,000 year literalists, and that's fine. And so, but the Big Bang says it's the universe. He gives an age of the universe, 14 billion years old. Well, I don't think. This is for those of you that are in that. I don't think that the Big Bang contradicts that, because again, it still comes down to faith. And time, as we're going to see through this unit, is not a static thing. Time isn't as static as we think it is. It's very much changeable. And there's places in our universe that actually exist where time no longer moves. Okay? And so we can be moving through time, but there's places in the universe where time is no longer moving. Yeah, it's called the event horizon of a black hole. Okay? And anyway, that's a whole lot. Anyway, I don't know what I'm saying.
There's no page for
So
the
relative to
slide.
where he's sitting, we're going to go back to what we know. We're going to go back to what I told you. There's going to be more questions than answers today. Relative to where you're sitting, you're moving through time and not space. When you travel through space and time, you travel mostly through time. Think about it. You get up to get the bag of Frito-Lays between, timeouts and you're mad in whatever, 2016, whatever you're playing after school. Okay? How much did you actually move compared to the expanse of the universe?
Like billions.
5 minutes.
Hardly any. We are time creatures. We mostly just move through time, hardly any space. Hardly any space at all. Even like if we were going to go to Mars, we didn't hardly go anywhere compared to the expanse of the universe.
We are like.
All right, now, if you were to travel at the speed of light, you would travel through space and no longer travel through time, thus making distances shrink. Okay, so it's like the flip of what we are. And that's why it's one of the reasons it's so hard to understand light. So time dilation is the stretching that occurs when we move through space. Because when we move through space, we're moving through. When you're moving just through time, you start moving through space. You begin to stretch time. And we're going to talk about that over the next few days. All right, I got through.